Hello everyone, my name is H. Jawahar Reddy. I am from Information Technology branch, A section. Today my topic is NFA with epsilon transition and conversion of NFA with epsilon to NFA, and I am from Institute of Aeronautical Engineering. So first, what is NFS with epsilon transition? So non-deterministic finite automata with epsilon transition. We extend the class of NFS by allowing instantaneous epsilon transition. The automation may be allowed to change its state without reading the input symbol. In diagrams, such transitions are depicted by labeling the appropriate arcs with epsilon. Note that this does not mean that epsilon has become an input symbol. On the contrary, we assist that the symbol epsilon does not belong to any alphabet. So let us see an example. So this language is a power n, where n is even or divisible by 3. So n is even. N is even. For example, n is equals to 6. N is equals to 6. N is 2. It is even. N is 3. It is divisible by 3. N is 4. Even. N is 5. Not divisible by 3. So it is the non-deterministic finite automata with epsilon transition. So P with epsilon transition goes to Q and R and R1 and R. That's it. P with epsilon goes to P, Q and R, and Q with A input A gives to Q1, and Q1 with input A goes to Q, and the final states are Q and R. And R with input A goes to R1, and R1 with input A goes to R2, and R2 with input A goes to R. So this is the non-deterministic finite automata with epsilon transition, which is equivalent to this language where a power n, where n is even or divisible by 3. So for example, let us take a power 6. Okay, so p with epsilon and q with a 1a goes to q1, q1 with a goes to q, a. So these are 6 a's, so goes to q, which is the final state. So this is proving that this is equal. And let's take a power 5. Okay, a power 5, which is not even and which is not divisible by 3. So P with A, R with A goes to R1, R1 with A goes to R2, R2 with A goes to R, and then R with A goes to R1, and then R1 with A goes to R2. So which is not going to final state. So A power 5 is not in this language. So this is correct. So epsilon NFA is a quintuple. A is equals to Q, transition state sigma, transition Q naught initial, and F is final states. Q is a set of states. Set of states, and sigma is the alphabet of the input. For example, in the previous ones, the sigma is A, where alphabet of input is A, and q naught is the initial state. Q naught in the previous, the initial state is P, and F is the final state, is a set of final states. And this is a transition symbol, where is the transition function. P of Q is a transition function. Note, epsilon is never a member of sigma, and sigma epsilon is defined to be sigma union epsilon. So epsilon NFA. Epsilon NFAs add a convenient feature, but in a sense, they bring us nothing new. They do not extend the class of languages that can be represented. Both NFAs and epsilon NFAs recognize exactly the same languages. Epsilon transitions are convenient feature. Try to design an NFA for the even or divisible by 3 language that does not use them. You need to use something like the product construct union closure of DFS. So epsilon closure. Epsilon closure of a state. The epsilon closure of the state Q, denoted E close of Q, is a set that contains Q together with all states that can be reached starting at Q by following only epsilon transition. So first let us see P. So P with epsilon transition. P with epsilon transition E close goes to Q, first P itself, then Q, then R, and then S. It also goes to S. So with only epsilon transitions, P can reach to Q, R, and S, and P itself. And epsilon closure of R is R itself, and then S. And epsilon closure of X is X itself. For the remaining 5 states, Q, Q1, R1, R2, R2, there is no epsilon transition. Compute the E-close by adding new states until no new states can be added. Start with P. Computing epsilon closure. Add Q and R to get PQR. Add S to get PQRS. No new states can be added. So given an epsilon NFA n, this construction produces an NFA n dash such that L of n dash equal to L of n. The construction of n dash begins with n as input and takes 3 steps. Make P an accepting state of n dash if E close of P contains an accepting state of n. Add an arc from P to Q labeled A if there is an arc labeled A in n from some state in epsilon closure of P to Q. Delete all arcs labeled epsilon. So first, so this is the NFA with epsilon closure, epsilon transitions. First, what we do is make P an accepting state of n dash. If E close of P contains an accepting state of n, so it is consisting an accepting state of n. Then what we do is we make P as a final state, P as a final state, and then add an arc from P to Q. Add an arc from P to Q. Labeled A if there is an arc labeled A in from same state in epsilon closure of P to Q. Then we convert this as this where we directly take the piece A to R2 and then delete all arcs labeled as epsilon. We delete all arcs labeled as epsilon and convert them to A, which is directly converted to A. So this is the final NFA without any epsilon transitions. So let us convert the NFA with epsilon transition to NFA without epsilon transition. So let us take the input. Zeros and ones are inputs and the states are A, B and C. Okay. So first epsilon closure with input first with input 0 A epsilon again epsilon closure. So A with input A's epsilon closure is A itself, B and C. So A, B and C. So A with input 0 goes to A itself. B with input 0, nothing, 5. C with input 0 goes to C itself. So A goes to A, B and C. And then 5 goes to nothing. And then C goes to C itself. So which is A with input 0 goes A, B and C. So then A with epsilon closure of A is A, B and C, and with input 1, with input 1, A with input 1 goes to nowhere, B with input 1 goes to B itself, and C with input 1 goes to C. Okay, so epsilon closure of I is nothing, epsilon closure of B is B comma C, and epsilon closure of C is C, so which is equal to B comma C. Okay, then now let's erase this. So now let's see B. So B, the epsilon closure of B is B and C. Okay, and B with input 0 is 5 and C with input 0 is C, so it is nothing, and C epsilon closure is C itself, so it is C, and B with input 1, B's epsilon closure is B comma C as we know, and B with input 1 is B itself, and B with C with input 1 is C itself, that is equal to B comma C, epsilon closure of B is B comma C, and C is C, so which is equal to B comma C again, and then finally C with input 0, C's epsilon closure is C itself, with input 0 goes to C itself, and the epsilon closure is C, and C epsilon closure is C, and with input 1 goes to C itself, and the epsilon closure is C, so it is C and C. So finally the NFA with no epsilon transitions is the transition table for non-epsilon transition uh, with no epsilon transitions is this, and let's draw the NFA diagram. So A, so what is the final state? Final state is that containing C, all are the final states, A, B and C are final states. So A with input 0 goes to A itself, B A with input 0, B with input 0 goes, A with input 0 also goes to C. Okay, A with input 1 goes to B, A with input 1 goes to B, and A with input 1 goes to C also, and then B with input 0 goes to C, B with input 0 goes to C, and B with input 1 goes to C and B itself. Okay, then C with input 0 goes to C itself and 1 itself. So this is the NFA without epsilon transitions. So thank you.